Okay, so I've started grading everybody's daily work and exam. So hopefully I'll have everything done by Thursday. I probably want to get it done by tomorrow, but be on the lookout for that. What else do I have to, oh yeah, and I went ahead to the 3 lectures we've had already. I went ahead and add timestamps to all of them, so you don't have to watch the whole hour and 20 minutes to figure out like what section we're talking about. So after when I upload it tonight, I'll go through and timestamp it so you can see exactly, when we're talking about section 6.6, 3, right? So you can go on to the YouTube playlist again, the link's on Blackboard, and then you can just use the timestamp to figure out where you want to go, so you don't have to listen to the whole thing. Are there any questions before we get going? So I'm gonna pause and do the timestamp over here so I don't have to watch the video and do it later. Okay, so if there's no more questions, we're covering section 6.6 and 6.7 today. Again, it's quite a lot of material that we're covering, but next week starts the regular week. So then we're going to be doing less every day, which will be a little bit nicer, like each lesson. So keep that in mind. It will get a little bit slower there. The next exam, if we wanted to look, just so I know everyone just took it, but we can go and look here. I had this open, but my computer started to freeze. Okay, so yeah, here's what we're doing. So the next exam isn't until week 13, so it won't be till sometime next week. So you can be prepared for that there. So it'll be week 13. So today we're covering Monday and Tuesday. Again, this is, you'll have daily work over tonight or over today's, over this and that, and then you'll have another daily work Tuesday and another daily work on Thursday, all due this coming Sunday. So, it'll be due every Sunday. The daily work we have worked on is due Wednesday. So are there any questions over that stuff? Okay. Again, everything should be back and graded to you by Thursday. So I'm starting on that now. Okay, so it didn't sound like anybody has any questions over previous work. So let's start with section 6.6 here. This is division of radicals and rationalization. So we're going to define what each one of these means. I'm going to put this here. Okay. So first things first is we have simplified form of a radical. So remember that the radical here, right, is talking about like the square root of 2, right? The square root of 2, it's the second root, you're taking the square root of that. This is simplified. So there's nothing more we can do to this. Now, on the other hand, if you had like the square root of 8, if we go back through to the other sections, you know that this is going to simplify to 2 square root 2, right? So it's good to know when something is simplified and when it isn't. So that is what this is talking about. Okay, so let's just kind of define, because it mentioned this last section, but I didn't show you this graph, but I think it's pretty important now. Okay, so number 1 says that the radicand has no factor raised to a power greater than or equal to its index. Okay, so I just wanted to go through like what that means. So looking at 1, it's saying if you had, let's say, the cubed root of y to the 7th. Okay, so notice that what number 1 is saying is the radicand has no factor raised to a power greater than its index. So this isn't simplified because the power here, which is 7, is greater than the index of 3. So that means this isn't simplified because we can write it as the cubed root of y squared to the third power times y to the first, right? That's one way we can simplify it, and then you can separate it like so. And we end up with y squared times the cubed root of y. So that is what number one is talking about, right? We can simplify this further because this power is so large, right? So that was something we've done before. The radicand does not contain fractions. So again, the radicand, which it's mentioned here, that's talking about the number underneath the radical, right? So y to the seventh is the radicand. The index, if you had y cubed x, the index is talking about what the root is, right? So in this case, the index is 3. Okay, so what number two is talking about is the radicand isn't a fraction, right? So if you had something like the square root of 1/2, that isn't simplified, right? And then we've got a property that can help us here. Let me move this down a little bit more. Okay, sorry. Yeah, so this can be simplified to square root of 1 over the square root of 2. Let me add a little space in between. Okay, we'll try that again. All right, so if you had the square root of 1/2, that isn't simplified. That's what number 2 is saying. So that means you can separate it. And not the best example because we actually have this, right? We have 1 over the square root of 2, which is what number 3 is talking about. So number 3 is saying the radicals are no radicals in the denominator. So that means 3 is actually what we have here, right? And what we're going to learn today is, and I'm not going to do it right here, we'll need to rationalize. And so that is what that is talking about. And basically, when we rationalize, that's going to give us square root of 2 over 2. And again, we'll define that here later on. Are there any questions over what number 1 is talking about? Okay. I'll move down just a little bit to here. So what the second part of this section is referring to is the division of property of radicals. So remember, we've had this property before, right? It's saying that, you can read the definition. We've defined it a couple of times. It's a little hard to see, but the property is saying that if you had, I think it's n, the nth root of a divided by b, that is equal to the nth root of a divided by the nth root of b. It's an n. Right? So that's just a property we've had before. Now, we can do a couple of these examples. Move down just a little bit further. So here we are. We have this here. Now notice that this isn't simplified. Remember the rules that it talked about? This isn't simplified by 1, or no, this would be, well, by 1 and 2. Right? We have a fraction, and then the power can be reduced here. Again, you're not going to be asked to say which rule it's not following, but just good to know that we're not done with it right now. Okay, so again, we can apply this rule up here, right? We can separate them. So now we've got the square root of 25 divided by the square root of 36. Now, these are both perfect squares, and so you can evaluate them. And the square root of 25 is 5, and the square root of 36 is 6. So that means our simplified answer here is 5 over 6. That was kind of a review. I think we did that last class. But yeah, are there any questions over this part so far? Okay, so let's look at this example. So I used to point out whenever we had daily work problems. Here is a daily work problem. So I didn't want to change the formatting, but you're going to have 7 questions on your daily work that's due this coming Sunday. And this is exactly like the first one. The number won't be the same, but it'll be similar to that. So when you see that, you know, this is a daily work example. So we'll see 7 of them here throughout the lecture. Okay, so notice that we can't simplify it any further. Right now, the square root of 63, you could break down a little bit more. But let's do the reverse of this property, right? So instead of having them separated, let's combine them together. So that means now we've got the square root of 63 divided by 7. What is the square, or what is 63 divided by 7? Anyone in the chat? Real quick, math whizzes, where are you at? Did we get 9? Yeah, I think so. I actually can't see, the chat's too far over. Right, it is 9. Thank you, everyone. So we get the square root of 9. Now notice that was a little bit easier, right? We didn't have to really separate anything. We could just divide them and get a nice whole number. So be on the lookout for that. That's one method you can do. So the square root of 9 is 3. And that is what that reduces to. Okay, let's look at one more example from this section. I'll move it down to about here. Okay, so here we've got the square root of a to the 6th and b to the 4th. Now, again, we're taking the square root, so our index is 2, right? So here, there's no way we can reduce this. We've got a to the 6th divided by b to the 4th. So we can't divide this, not like we did here, right? So what we can do is separate them. So we've got the square root of a to the 6th power divided by the square root of b to the 4th. Okay, so this is kind of a review here. We need to match the power with the root. So that means square root, and this is a to the 3rd power raised to the 2nd, right? Again, just kind of a review, right? That this is another way to write it. Right? You've got a to the 6th, and the question is, right, we want to raise it to the 2nd power, right? So be thinking 6 times what gives you, excuse me, what times 2 gives you 6? And the answer is 3, right? Because you multiply these together. So that is how we broke that apart. If we just carry on the equal sign, we'll do the denominator here in a second. So again, these undo each other, right? So we're left with just a to the 3rd. Be thinking of how you could break apart b to the 4th in a similar manner. This is b squared to the 2nd power. Again, I think this was one of the first topics we covered in the class, being able to separate it and simplify it like that. So this becomes b squared. And there is your answer. Are there any questions over these 3? Okay, seem okay. Okay, move on here. All right, so I'll move down just a little bit. I gave a lot of room here. Okay. Again, this is the very same definition that was up above. So if you copied the one from above down, don't recopy this. It's the same one. But now this third section here is rationalizing the denominator with one term. Now, that is dealing with this requirement here. So rationalizing is working with that. So let's look at an example. Thought I had, I don't have an example here. Okay. So this is your second daily work problem. Move this up just a little bit. We want to rationalize this denominator. So notice we've got a fraction again inside the square root. So what we can do is break up the fraction here, right? So we've got the square root of 2 divided by the square root of 5. So remember what happens if you were to take the square root of x times the square root of x, right? You take the same radical times itself, and you multiply the insides. So this is now the square root of x squared, which reduces to just x, right? So this was property talked about last time. So that means we got to figure out, well, if I wanted to get rid of this square root of 5, what would I have to multiply to it to undo the square root of 5? Well, what we would have to do is multiply this by square root of 5, right? But if we multiply something in the denominator, we have to do the same thing to the numerator. So now this is also square root of 5. So multiply square root of 5, both top and bottom, right? A little multiplication sign there. In the denominator, you have the square root of 25, and in the numerator, you'll have the square root of 10. Remember, you multiply the radicands together. Okay, so the denominator is now just 5, and that's exactly what we wanted, right? We wanted to get rid of this square root in the denominator. So this idea of rationalizing does that for us. The numerator is just square root of 10. So real quick, think to yourself, can the square root of 10 reduce any further? See what you think here in the chat. Can I reduce the square root of 10? Or are we done? What do we think? 2? So can we reduce the square root of 10? So we got no, yes. How about a third person? Or I don't know, that works as well. Okay, so this is actually simplified. Now let's take a look why we're done here. So this is, we're done, but why? So again, if we look at the square root of 10, right, that's the question here. I can't find, shouldn't have changed the color, one sec. Okay, because the square root of 10, well, hold on, before we write it like that. When in doubt, if you're not sure if the radicand can break down more, look at the prime factorization, right? Well, the prime factorization of 10 is 2 and 5, right? But notice both of these are prime numbers and they're not perfect squares. So the square root of 2 and the square root of 5 cannot be simplified any further. So we can say these are prime, or not perfect squares. So we're done. Now, just kind of reviewing here. The perfect squares are, so if you want to know if you can reduce it, be looking for these numbers. See if they're hidden inside of the numbers here. If you had 4, 4, 9, 16. Well, here, hold on. Let's look at it like this. A perfect square is any of these numbers multiplied by them or multiplied to themselves, right? So a perfect square would be 4, 9, 16. Oh, I see that 5 and 6 are pretty much on together there. And 25, right? These are the things you should be looking for. So if your number can break up into any one of these, you can reduce it further. So that is the idea for these perfect squares. Are there any questions over this idea of why we're done with that? So that there is your answer. Okay, we'll move on. We'll leave it to about right here. Well, hold on. Let's evaluate this here. Okay, so again, we need to rationalize the denominator and then simplify further. So again, we have this fraction underneath the denominator or underneath the radical. So let's, can we reduce the fraction? No, right? Y to the fifth can't divide into, or 7 can't divide into y to the fifth. So there's nothing we can do there. So we can look at y to the fifth divided by y to the seventh. Now, again, your index here is 2, right? So you're looking for a power of 2 that can undo the square root. Now, let's look at what we can do. Well, first, let's just rationalize. We'll worry about simplifying here a little bit further. So just like up here, we multiply by a square root of 5, because if we multiply by the same thing, it'll undo that, right? We want to be able to undo the square root. So here we can multiply by the square root of 7. Now again, if you multiply in the denominator, you have to multiply in the numerator, right? Because the square root of 7 times square root of 7 will just give us 7. So in the numerator in the top, we've got 7 times y to the fifth. In the denominator, we now have the square root of 49, which we could look at it as square root of 7 times 7, which is the square root of 49, right? But the nice thing is we multiplied it by that number because it'll reduce down to just 7. So now we have to look, is there any more that we can do? Well, there is, right? Because this right here has an index of, oh, I just erased it. This has an index of 2 because it's a square root, right? So notice that your index is 2, but you're raising it to the 5th power, right? So this is larger than that. So we can continue to simplify down. So let's look at a nice review again. So draw an arrow up here. That looks good. Y to the 5th, right? Remember that we want to break it down into something to the 2nd power. Again, now it's an odd power, right? So right, we're looking for what number goes up here. Now, we couldn't have 3, right? Because 3 times 2 is 6. That's too high. So we could go 2, right? This will give us y to the 4th, but then we also have an extra y out there. Right? So anytime you have an odd number or an odd power, right, and you're looking for an even root, you'll have to separate it like that. So if we substitute in what we found, what we've created here, get y squared, the 2nd power. Oh, let me write 7 first. So you got 7 times y squared. Again, I'm showing a lot of work here. you know, if you start seeing a pattern, go to that pattern. You know, it'll help here. Okay, so I'm actually going to go down here, and again, we have only one thing that can come out of the square root, and it's this y squared to the second power. That's the only thing that can be evaluated. So what we have here from this line down is we're saying that we've got the square root of 7 times y squared squared times the square root of y, right? I just separated all these, and this is the only thing we can evaluate, right? That comes out as just y squared. So we have y squared times the square root of 7 times y, all divided by 7. And that right there is your simplified radical expression. What questions do we have over this question or this example here? Okay, I'm going to move on. There's no questions, immediate questions. I gave one more example. Now, this one here's a little bit different. You know, notice that you've got just a little bit. Why did the... Okay, so the question was, why did the square root, this, move outside of the square root? It's because you can evaluate it. Like we know what the answer for this, like this square root is. Like anytime, because you've got an index of 2, right? It's a square root. You can think that this square root, the root and the power undoes each other, right? So like this cancels out and you just get y squared. In this case here, it's 7 to the first power. I don't like that. It's 7 to the first power and y to the first power, right? So these can't, you know, they can't come out from under the square root. You can't evaluate them. So that is why only y squared does, right? So this is equal to just y squared. So then you've got these two that you multiply back together to get 7y, and this is just y squared, so it comes out in front. Did that? Okay. Again, yeah, if you have any questions, just stop me here. I've got the chat open so I can see here. Okay, so here we've got 5 over the cubed root of a. So now we got to figure out what we need to multiply to undo the cubed root of a. So let's look at this. You know, the pattern has been, well, we just multiply it by the same thing, right? And it undoes the root. But what happens if we multiply by the cubed root of a? Let's take a look. Why this wouldn't work. So if I do that, again, the numerator stays the same. Now down here in the denominator, I'm going to have the cubed root of a to the what power? Right, this is the cubed root, but what power are we going to have it to? What do we think? I have a times a, which would be a squared, right? So here, the power wasn't large enough, right? This wouldn't work. Right, there's no way to evaluate the cubed root of a squared. So what we need to do is use a higher power here. I can't see if it's going to work. So let's try a different one. Let's see if we can. There we go. Okay, so this doesn't simplify, right? So we can do one better. Right, let's try to go 1 power higher and see if that'll work. So here, instead of the cubed root of a, we can go the cubed root of a squared. Now, why will that work? Well, move down just a little bit further. We multiply these, right? This is now the cubed root of a times a squared, right? So now in the denominator, we've got, just to make it a little more clear, I'll match the color here, right? This is a squared. Okay, so the reason this will work is because this is a to the first power and this is a to the second power, right? So when you multiply the powers, you add them. So this is now the cubed root of a cubed, right? Up here in the top, you can't multiply this, these together, or you can, but the 5 just goes out in front of the cubed root, a squared. Okay, so again, you've got matching powers. You've got a power that matches the index, and so this undoes that, and we get the rationalization that we need. So we just get a, and this right here is your final answer. So notice you don't always multiply by the same thing. In this case, you've got a third root, so you need to match that root underneath the radical, right? So that's why we chose an a squared, because a times a squared is a cubed, which undoes that. Any immediate questions over this? What do you think? That's about right there. Top. Oh, good question. Oh, we shouldn't have. I wasn't paying attention. Good catch. Yeah. Notice you multiply the same thing in the denominator and numerator, so it should be the cubed root of a squared. Thank you. Okay, so the other type of rationalization problem is one where we've got two roots here, or we've got two terms, right? Here it was just an a cubed, here we've got 5 minus 2 square root 2. So in these type of problems, this is going back to the last daily work that we talked about. I'm going to move this down just a little bit so it's not so involved there. We're going to be looking at the conjugate. And so, just a little bit. Okay. So this is a bit of a review from last time. But we want to see if you just multiplied, again, if you're writing this down, don't write this next part down. I'm just going to show you why we can't multiply by 2 square root 2, right? Well, why won't that work if we multiply the numerator and denominator? Well, hopefully you see that when you distribute the 2 square root 2, right, that's saying that you're multiplying, I like drawing this arrow, so we're going to do it again. Right, the reason this won't work is when you distribute this, you're still going to end up with a radical underneath the square root, right? This now becomes 10 square root 2. This, on the other hand, is now -4, multiply the 2's out in front, and the square root 2 square root 2, which is square root of 4, right? So it doesn't get rid of the square root, which is the whole reason we're going through this, right? Is we want to get rid of that. So don't know why I'm going through all that work to write it, right? This won't work, right? We have to find something better, something better to multiply this by, so we completely get rid of the square roots. Now, what we're looking for, the term starts with a C and it ends with 8. Does anyone remember what that is? While I erase this. Okay, so what we need to multiply this by, I'm going to go ahead and write it up here, is the conjugate, or conjugate, I guess. My hint wasn't very helpful. So what the conjugate is you have 5, 2 square root 2, but now we need to multiply by not a minus 2 square root 2, but a positive square root 2. And so this right here, I'll use like the cool marker. This is the conjugate. Look how fun that is. And so, yeah, let's look at like why that is what we're looking for. So I'll draw like, right? So the conjugate means that we're going to, whenever we distribute this, right? The 5 goes to the 5, 2 square root 2. We now have 25, was it plus 10 square root 2, right? The 5 plus 2 square root 2. Let me match the colors so it might be a little easier to follow. So we got 25 plus 10 square root 2. Distributing the rest, I think, no, blue maybe, we'll go with that. We've got what? Negative 10 square root 2, and then this last one is positive 4 square root of 4, right? So multiplying those. The reason the conjugate is nice is this middle term goes to 0, right? So you end with 25 plus 4 square root 4. Now the square root of 4 is 2 when we evaluate that. So we've got 4 times 2, which is what, 25 plus 8. 25 and 8 is 33. We don't really need to box that. We just get 33. Okay, so before we start this problem, are there any questions over this conjugate business? Okay, this is, I believe, section 6.5. I think that is when we talked about that. So we were just multiplying this separately. So if you haven't done the daily work from last Thursday, that is what this is about. And I think that is what that is. Okay, so the conjugate is what we need to multiply by, because we're going to completely get rid of the square root. As we can see, we come down to just a nice whole number here, 33. Okay, so that is what we're going to multiply this by, is the square root, or 5 plus 2 square root 2, right, the conjugate. So again, multiply the top. Now we're multiplying a binomial, so we've got 2 terms to multiply. That means that we already know what we get here, right? We get 33. That's from the work over here. Now up here, it would have been nice to have some room to write it up top, but there was none. So negative 7 times the quantity 5 plus 2 square root 2. That is going to be, distributing this to each one, is negative 35. Now, I hadn't really shown work here, but you only multiply the number out in front. The square root 2, you would only multiply if you had another square root of 2, right? So because we don't, or another square root in general, right? You can multiply square roots together. But this just becomes negative 35, multiply the negative 7 and 2, we get negative 14 square root 2. And so that is what goes up here. Let me make that a little bit larger under here. Okay, are there any questions so far? What you need to look for now is, can you simplify? Is there anything that divides these 3 numbers, right? So you're looking, is there anything that divides 35, 14, and 33? In this case, there isn't. you could go through your, oh gosh, you could go through your multiples, but there would be nothing that would multiply the or divide these three numbers, right? So this right here is your simplified answer. Questions before we go on to the last section, which is 6.7 of today. Okay, like I said, some of these problems get kind of involved, right, with the conjugate. There's a lot going on, so make sure you're comfortable with the previous sections here. Okay. So I'm going to go down just a little bit further to right there. Okay, so this is section 6.7, and now we're solving radical equations. Everything we've done up to this has just been expressions, right? There's been no equal signs. Oh, why multiple with a positive? Okay, it's because of the conjugate. It's a special number that we multiply by. Right? If I had, let's say, let me do one more example. We won't go through like a whole problem like that, but if you had, let's say, -3 plus square root of probably not a nice number. Let's do square root of 2. What you the conjugate, which is what we're looking for, you know, we could say like 2 over -3 plus square root 2, right? We want to rationalize so we don't have a square root in the denominator. So the number that you need to multiply by, top and bottom, this is called the conjugate. So that means it's always your second number is going to be negative. The reason being is you want to cancel that middle term, right? You can think, let me go ahead and write it, right? You can think if you had something like x plus 7, x minus 7, this positive and negative is going to cancel that middle term, right? And that middle term is where you're going to get your square root at. So by multiplying with the positive and negative, you cancel your square root and you end up with a nice number with no square roots in them, or radicals, depending on whichever one you're solving for. So multiplying this out, you'd end up with 9, right? This and that. Now the outside and the inside, that makes any sense. The two outside numbers, which are -3 and negative square root 2, that cancels with -2 times square root 3. Square root of 2 times -3, right? So middle terms cancel, so you end with just the negative, because now we're looking at, let me cancel, or use a different color, right? Because these two, yeah, will give us what, negative square root 4. Yeah, and the reason it's so nice is now we've got 9 minus 2, which is just 7. So the conjugate, yeah, gives us a nice number with no square roots. So when you need to rationalize, that is a step there as a conjugate. Good question. Any other questions? Okay, we'll go ahead and move on. There's a few examples here in section 6.7. So I can't remember how many of the daily works we've been through so far, but there's 7 total, and we'll get through all of them. Okay, so solutions to radical equations. So we need to be able to solve this here. So remember that if you had something like the cubed, let's not do that. Let's do the 5th root of x to the 5th, right? So your index and your power match, so you get some nice cancellation. We have done, oh, thank you. So we've got 4 more examples for sure that are through here, but we'll cover all 7 before we're done. So you can refer back to the lecture, your notes. Thank you. Okay, so notice that these undo each other, and so we get just x, right? It's a similar idea here, where if we want to undo the cubed root of x, right? Right, because we want to get x by itself, that here we're going to raise both sides. Well, here, let me do it separately here. Okay, so to solve this, is you want to raise it to the power that matches the index. So here, raise it to the third power. So just like here, when your index and power match, it undoes the radical, and you get the number free from that. So here, raising this to the power of 3, you now have x and 5 to the third power, right? So we got to figure out what 5 to the third power is. That's 5 times 5 times 5, which is 125. So you can, thank you. So you can check, you should get 125. Now, before we're done, we have to make sure that there's no extraneous solutions. So, and you'll see that in this little step-by-step thing that we've got down here, that we'll need to check that too. So, is 125, oh my gosh, I don't know why I would want to try to spell extraneous. The question is, does 125 work? Right. Thanks for no one spelling extraneous in the thing. That would have made me feel bad. Okay, so plug it back in. So you need to see if this works. So that means, is the cubed root of 125 equal to 5? Well, it is, right? Because 125 we just saw is 5 cubed. And you might think, well, this is kind of redundant that you're going back through here, but this is now 5, right? Notice the cancellation is now on the inside, right? The power is in the inside of the radical. Oops, put a little check mark. So yeah, that is your solution. So for each one of these, you're going to have to plug it back in and make sure that it works. And we're going to see an example where it doesn't work, and hopefully you'll see like what to look out for when that doesn't. Any questions over this so far? Okay, so here we have step-by-step ways of solving a radical equation. Now, this will work for all of the other examples we're going to have here after this. So step 1, I feel like that's kind of small to read. Let me get a little bit larger. Okay, so if we can read that. So step 1 is you isolate the radical. If an equation has more than one radical, choose one of the radicals to isolate. So we just need to get the square root or the cubed root by itself, right? So step 1 was already done for the first example. Step 2, move down just a little bit further. Oh, too many. Well, okay. Step 3 is raise each side of the equation to the power equal to the index, right? That's what we did. We chose raising it to the third power because it'll undo the cubed root. So that is what the second step is. Third step is solve the equation. Just a little bit further. If the equation still has a radical, repeat steps 1 and 2. So that means that after you raise it to the power, you could still have a radical, so you'd have to do it again, right? So if doing steps 1 and 2 don't completely get rid of radicals, you got to work that again. So that is step 3. So you'll always need to do steps 1 and 2 to get rid of a radical, to undo a radical. Step 4 is check the potential solutions in the original equation, right? So we checked 125 to make sure it worked. So you're probably asking yourself, when does it not work? So let's look at this, right? Let's solve for the square root of 2. So be thinking, what do I need um, what do I need to raise both sides to undo the square root of x? What do we think? Anyone have an idea while I recopy this down? What should I raise both sides to undo an index of 2? Okay, hopefully everyone has thought, and it's a 2, right? Because the square root, that is the second root, so squaring both sides undoes that. So now, this undoes the square root, so we now have x is equal to -7 times -7, right? So negative times a negative is a positive. Okay, so hopefully you see why this isn't going to work, because if you plug it back in, so we need to check to make sure that it works. Well, this example doesn't, right? Because the square root of 49 is a positive 7, and that is not equal to a -7. So this actually has no solution. So it's always important to check to make sure that your solution works and it's not extraneous and when we throw it out. Probably to be a little more accurate, you'd put no real solution. Okay, are there any questions over what we covered so far? Be thinking, I'm gonna move it down just a little bit further. Okay, so this is actually our last section. So the second one is just solving radical equations. We're gonna see, I think, 4 or 5 examples that look a little bit different each time. So we're almost there. So moving down a little bit further, we have section 2 is solving a radical equation involving one radical. So really the first 2 examples we did matches this description. But we need to solve an equation containing one radical. Just repeated myself, but that's okay. So to solve the equation, remember what those steps we're talking about, right? We need to get the square root by itself. Right? So that means we can subtract 5, both sides. Right? We want to get this square root p by itself. So this becomes square root p. 9 minus 5 is 4. So we get that. Again, we need to undo the square root. After saying root a lot, or root, I feel like I'm mispronouncing it. So we raise 2, right? Because this right here is the second power, or I mean the index is 2, right? That is why we're raising it to the second power. Okay, so now we have p is equal to 4 times 4, which is 16. So again, we can check. So when you check, let's say, well, is the square root of 16 plus 5? What does that equal? Well, the square root of 16 is 4. 4 plus 5 is equal to 9. So yeah, square root of 16 is our solution. Move up a little bit further. Okay, so the fourth type of problem you'll see on your daily work, whether it's on Alex or on Blackboard, you can find it either place, is something that looks like this problem, right? Is we want to solve for x given x is a real number. You can't have a negative number underneath the square root or any even root. So again, our first step here is we need to subtract by 1. We want this square root by itself, right? Step 1 is telling us that we need to isolate the square root. So move it down just a little bit further to right here. Now, again, just like up top, we needed to subtract to get the radical by itself. So subtracting 1 on both sides, we now have this entire radical here, right? Square root of 2, and that's going to be equal to 2. Again, we need to undo a square root, so that means we're going to square both sides, raise to the second power. Okay, so raising to the second power, the right side is equal to 4. Now this side here, it undoes the radical completely. So now we just have 2x plus 12. Okay, so now we need to just work this like a regular linear equation here, right? So subtract 12 on both sides. We have, this is -8. We got 2x. Okay, so the final step here, right, is divide by 2. Okay, that means x is going to equal, oops, -4. Divide by 2 on both sides. We get x is equal to -4. Before we say that's the solution, right, we gotta plug it in, right? Make sure this works. So again, when we check, um, anytime you check an expression, choose like the left side, plug it in, and see if it equals the right side, right? Or you could do something, another way that you could check is have both sides like that, and then because we're not quite sure, put a question mark, right? Does this equal 3? So I'm plugging in -4, right? You can't have a negative underneath the square root, but let's see what happens. All right, so this now becomes -8, just taking this here, plus 12, right? We're not quite sure if that's equal yet. This right, oh, forgot the 1. So -8 plus 12 is the square root of 4. I don't really like doing this method. My question marks look worse and worse. This becomes 2, and 2 plus 1 is equal to 3. So this is indeed your solution. Questions over this example? Seem okay? Okay. You're still writing it down. I'll let you get that down. Move it just a little bit. See how far down we are here. Okay, so the next type of example, again, it's similar to this, is it might be written in exponent form, which in my opinion, having it in exponent form makes way more sense of why we raise something uh, to the power that we do. I didn't show this. I know I did last semester for beginning algebra, and I think I made it more confusing, so I've just left it out. Move down to about right here. But we need to evaluate this, right? So if you see this type of example, I just want you to know that you can convert back to the square root form or the radical form. So remember that when you have a exponent, a fraction in your exponent, it's actually a radical, right? You can interchange between the two forms. So this is now, um, anyone want to say where the 4 goes? Is it the index or the power? What do we think? Anyone remember? You got a 50-50 shot. Power, index. It is the index. Right, it's kind of 50-50 with it. So the way that I remembered whether it's the power or the index is I memorized one case. When I was taking this, I always got it confused. So how I remembered was I only remembered one case. I didn't remember like the, oh wow, that's really bad. Um, I only remembered one case, and that helped me. I remembered x to the 1/2 power is equal to the square root of x to the first. As long as you remember one case, then no matter what the numbers are, it'll always be in that form. So that's just what I chose to do. It was just a way to, instead of memorizing um, the a to the n over m is equal to the mth root of a to the n, which I think can get kind of confusing. Just memorize one case, and then you can use that case to kind of remember all the other ones. Okay, so you have 1/4, so 1 is the power, and 4 is your index. So you can swap in between there. So again, right, this is the same thing as 7 to the 4th root of x plus 3 plus 9, right? So they mean the same thing, so you can go in between square roots and radicals. Now, before we continue, I just want to say, like, well, what if we, like down here, right, what we'd have to do is subtract 2 on both sides, or what you have to do down here is subtract 9 on both sides, correct? To get the square root by itself, right? Just kind of what we've been doing, subtract 9 here, subtract 9 here. Okay, well, we do the same thing up here, right? I'm not going to solve both, but I just want you to see of another way of looking at these problems. So you've got -2 is equal to the quantity x plus 3 to the 1/4 power, right? Now, we would raise it to the 4th power, right? We want to undo a square root of 4. So notice that whenever you multiply, oh, hold on, you raise it to the 4th power here and to the 4th power here, you know, this right here, your 2 powers, nothing like orange and yellow going together, right, this is the same thing as 4/4 or just 1. So that's another reason why it undoes that power, right? So this is the same thing as -2 to the 4th. We still have to evaluate it, but this is now just x plus 3. So that's another way to look at the problem. You can do everything with fractional exponents. You don't necessarily have to have it in radical form. I prefer fractional exponents myself, but okay. Any questions over what I did while I mess with all this stuff? Okay. Right. So I just wanted to show you guys that example in case you saw something like that. Okay. So continuing on, we have another example, and this one's actually your 5th daily work problem. Okay, so notice that you've got 2 square roots now, right? You've got it here, there, right? So we got to figure out, like, well, how are we going to do this? Well, remember what rule 1 said. You have to isolate one of the square roots. So notice that this square root is by itself, right? You've got the radical x plus 56, right? It's by itself. So what that means is we can go ahead and square both sides, right? That'll undo this square root. So this problem here, same method, but it looks a little bit different. Okay, so let's write this. Let's go ahead and put equals here. So oops. Just so we kind of see what we began with here. Okay, so here we are. We square both sides. That means you square the entire left side and the entire right side. That's why we have the square root of 4 plus 4 in parentheses, right? We square both sides. Okay, so what's nice is this right here becomes just x plus 56. This, on the other hand, we got to figure out what the square root of 4 plus 4, wait, oh, hold on, that's an x. Thank you. Making sure you guys are paying attention, that's what it is. First mistake all year. Okay, so we got to work this, right? So scratch work is, let's figure out what the square root of x plus 4 times, well, hold on, before we do that, squared. I didn't want to skip too many steps here. Right, so basically we're going to work this separately. This, again, I think is from section 6.5. I don't know for sure, but I think that's what it is. Right, it's similar to how we did the conjugate up there, but it's not the conjugate, right? We're just multiplying this quantity by itself. So when we do that, square root of x times square root of x times x, this becomes the square root of x squared, right? These two multiply together, plus 4 square root x, and still gotta move that over to the side. This now, let's choose purple. Right, this multiplies to those. Guess I could do it up above, might look better. Right, 4 to each one of these. So you have 4 square root x plus 16. So when we simplify this, sorry, it's not working. Huh. Okay, well, it's just going to be in purple because I don't know why it's not working. This right here simplifies to just x. Here, these two combine together to give you 4 or 8 square root x, and this is 16. So any questions over just that step there? Always seem pretty good. Okay. So let's go ahead and substitute everything in. I'm going to try to change this color here. All right. So if we plug that in, we've got x plus 56, and this is now equal to x plus 8 square root x plus 16. So notice this is where step 3 comes in, up above that what to do next, right? Because now we've got a square root of x, right? So now we have to do the same method again to get rid of the square root. So I meant to make that orange. Okay, so hopefully you're thinking what you'd subtract to both sides, right? So let's subtract x on both sides, right? So now we're going to have 56 is equal to 8 square root x plus 16. Now you can subtract 16, right? Because our goal is to get the square root by itself. This becomes, oh gosh, 40. Got some shortcuts on my little digital pad here, but I haven't set them up yet. Probably make everything go a little quicker. So we've got square root of x. Okay, so you could raise everything to the second power right now, but actually we can divide both sides by 8, and that'll actually make the numbers a little bit smaller to work with here. Divide by 8, divide by 8. So we have square root of x is equal to 5. So finally what we can do is take the square root on both sides, and that'll finish getting x by itself. So we get x is equal to 5. Again, we need to, oh no, it means x is equal to 25. There we go. So we need to make sure that these work here, right? We gotta make sure that this works inside the equation. Okay. So just like before, now we need to check. So you've got 25 plus 56. Now that is going to equal, what do we got here? 25, that's a 1. Carry it up there, 81. No, that can't be right. Hold on. Do it in my head again. So 1, is that 81? Oh yeah, it is 81. What am I doing? I've got a calculator right here. Right. Okay. I'm glad everyone got to watch me do that. Okay. So this is now 9, right? This is another way to check, right? This is saying the left-hand side of this equation up here is that. The right-hand side is what? So hopefully you're checking along with me. Right-hand side. Okay, that's saying what? Square root of 25 plus 4 is equal to 5 plus 4, which is 9. So 9 equals 9. We're good to go. So 25 is equal to x. Okay, so that question there was pretty lengthy, but you will have a problem similar to that. Again, I will timestamp it, so you'll be able to find this in the video. Jump right to this one if you need. Okay, I'm gonna go ahead and continue on. I'll move it down just to about right here in case you're still writing down the check problem. Okay, so the next type of problem is one where you have a variable on the other side, right? So now we've got v is equal to the square root of 9v minus 14, right? So we need to solve for v. Again, we've got a square root, so that means you can square both sides, right? So raise both sides square, second power. So I'm just gonna write it over here. Okay. So what we just did, right? Square both sides, square both sides. Here you end up with v squared. On this side, remember it undoes the square root, so you get 9v minus 14. Okay, so now we have to figure out what b's make this true. Notice that it's a squared, right? So it's a quadratic. So to solve a quadratic, we're going to need to get everything to one side and then factor. So here we've got v squared minus 9v plus 14 is equal to 0. Right, so I moved over all these terms on the right-hand side to the left-hand side. And there we are. Okay, so we need to factor it. Now, again, I'm not going to go through the work into factoring, but we'll talk it through here, right? Remember, again, that you have to have a v term is your first one, right? Because that gives you, oh, because I moved everything to the left-hand side. We did that because we want to factor this, right? And to factor, it needs to be set equal to 0. So let me go up here. So we've got, let me write this, we got a quadratic. It needs to be equal to 0. So that's why we moved everything to the other side, just to solve it this way. Okay, so we got v and v, that gives you v squared. So now we got to think of what number times itself gives you 4, or yeah, 2 numbers times itself to give you 14, but adds to give you -9. We can think. Perfect. -7 and 2, right? -7 plus -2 gives you -9. And it also multiplies to give you a positive 14. So -7, -2. Again, factoring will keep showing up. So the best way is just more practice if you feel uneasy on that. Okay, I'm gonna go ahead and move down all the way so we have more room to work. All right, so now we use the zero product property, which just says b minus 2, oh, let's do it this way. b minus 7 is equal to 0, and v minus 2 is equal to 0, right? So solving for both of these, right, add 7, add 2, we have v is equal to 7, and v is equal to 2. Okay, so we need to make sure that both of these work, right? That we get the number when we plug it back in. So just like we did before, we need to check and see if they both work or if they're both one or both are extraneous solutions. So let's let v equal 2. That means we've got 2 equal to 9 times 2 minus 14. We should have picked 7. It just seems like it would make more sense, right? The question is, are these equal? You know, I'm going to take that out. We're going to work down this side here. All right, so 9 times 2 is 18. So this becomes 18 minus 14. That is 4, which is 2. So 2 does equal 2, right? So the good thing is we know that 2 is an answer. All right, we got to do the last thing for 7. Yeah, I was going to skip it, but we're going to go ahead and show the work. I don't need to skip that. Okay, so now we let v equal 7. So I don't know which ways people prefer to check, but the left-hand side is equal to 7. Right-hand side is 9 times 7 minus 14. Well, I'm gonna scoot down a little bit further. Right there. Okay, so what? This is square root of 63 minus 14. Everyone do your mental math while I clearly use a calculator. We get 49, right? Yes, I agree. So 49, we end up with 7. So the left-hand side and right-hand side equal. So both 7 and 2 are solutions, right? So right-hand side is 7, right? So we're good. These are both of our solutions. So there was yours. Oh gosh. I'll edit that out in post. So that was your 6th example with Alex, or with your daily work. The final one we're going to look at looks like this, right? So here we need to again solve for u. It's kind of funny because I think this one is probably less work than the 2 we just did. But notice we've now got a 3rd root. So we've been dealing with square roots, but now we don't have that. So again, let's look at it. I hope everyone watches this video and they're like, he said he'd get rid of that in post-production, but I'm not going to. There's no way to cancel that out. Okay, or edit it out. So again, we need to solve for the radical. So subtract 3 on both sides. We have the cubed root of 6u plus 4. That is equal to 4, right? Subtract 3 on both sides. So to undo the square root, or to undo the cubed root, you need to cube both sides, right? Raise it to the 3rd power. So 3rd power here, 3rd power here. Okay, what is 4 times 4 times 4? Write this down. Right, that undoes that. 64, good, thank you. 64, right? So now, continuing on, subtract 4 on both sides. Oh, let me do it in orange. So hopefully you're working along with me. And you're like, wow, if he just wouldn't use different colors, he'd already be done. So you get 60, and that's equal to 6u. So dividing both sides by 1/6, you get, or multiplying both sides by 1/6, you get u is equal to 10. Again, we need to check to make sure that it works. So we've got the cubed root of 6u plus 4. Oops, plug in u. 10 plus 4. Right, this is going to equal 60 plus 4. 60 plus 4 plus 3, right? Or this is a cube root. So we have the cubed root of 64 plus 3. The cubed root of 64 is 4. We saw that over here, right? This right here was 4 times 4 times 4, or 4 to the 3rd power, right? That's 64. So the roots undo each other here. So we have just, well, I'm going to go ahead and write that out. I think it's good to see. Okay, so hopefully you see that it works, right? You have this right here is 4 plus 3, which is equal to 7. And that's exactly what we needed it to equal, 7. So u equals 10 is your solution. Okay, are there any questions over anything at the moment? What do we think? Okay, so this finishes the daily work for today. Again, all 7 questions will look similar to the ones we covered. I'll have this uploaded to YouTube later tonight, so you're welcome to check it there. I'll timestamp it in the comment so you can see that. Go through. Any questions over setup of the class or anything? Anything I can clear up before class is done? People are still here. Okay, all right, well, if there's no more questions, we're done for class. We'll meet back up tomorrow at 7:25. Yep, welcome. So again, everything should hopefully be graded and back to you by Thursday is my goal. 7:05. Thank you. 7:05, regular class time. Thank you. Yeah, you too. So see everybody at 7:05 tomorrow. Thank you. Have a good night. See you. Go. You stop.